SwayamPrabha. Digital India. Educated India.
So there are different ways of selecting the materials, a material selection method. The major thing is based on cost, as I told earlier, then comes weight, and then finally it is expert system which are available today in doing it. Cost is a term which is interrelated with performance. Okay. Then is weightages, weighted properties comparison. So that's what we do. First we said we will look at different properties, then we look for each property what is the weightage, and then we will try to do a selection of the product. The cost versus property analysis. In the present method, we are going to discuss a method. In the present method, we compare the material cost for equivalent material property requirements. For example, we take two different materials, take 50 kilos of load. So how do you choose A as compared to that of B? Okay. So the properties generally we talk about is tensile, compressive, flexural, fatigue, creep impact, and many more things to do. So the method determining the weight required for different materials need to meet the desired property. And from the weights, it determines the cost of the product. Last class we saw density related to weight fraction, and that in turn you can relate it to volume fraction. So this is what we saw in the last class, last derivation which I did. So now let us try to take a simple example and start working. Suppose we take two materials, alpha and beta, to meet the same tensile strength. So we need to understand density. Density will be rho alpha and rho beta. So since I want to find out the tensile strength, so I need to know the cross section area. So the cross section area of the material will be A alpha and B beta. Okay. So if we design for axial load P. So the cross section area of the beam. So we are trying. What are we trying to do? We are trying to do a beam analysis. Beam, right? Beam analysis. ANA analysis, right? With respect to cost. So the cross section area, the CS required for beam is, that means to say beam is like for A alpha, you try, that is load by sigma alpha, and beams I will make this as R. Okay. So A beta, what we have is, this is load by sigma beta. This is beta, sigma beta. So the assuming the beams are circular solid rods, because these are very easy to manufacture. So then what is the biggest thing which comes? The diameter. We have to the diameters of the beams are 1 d alpha square equal to load by area, that is nothing but 4p by sigma into alpha A. Then d square equal to 4p, which is nothing but pi beta. So here it is for beta material. Okay. So now what we have to do is, we have to reconvert this, and then, because I said it is for finding out for a for the same load. Okay. So for the same load, so if I want to write the equation, rewrite the equation like this, I can say it as, it is pi by 4 d alpha square into sigma alpha, that equal to pi by 4 d beta square into alpha beta. So what are we trying to do? We are trying to take two different materials. Two different materials will have two different densities, but the cross section area we assume to be the same. The loads are the same. So we are trying to find out what is the relationship between them. Okay. So the ratio of the diameter are, so it becomes d alpha by beta, diameter is nothing but a beta by a alpha, sigma alpha by 1 by 2. For equal length of rod L, the volume ratio, first then we have to find out the volume ratio of the rods will be same. So the weight ratio, what happens to the weight ratio? Weight ratio is nothing but W by alpha by W by beta equal to rho alpha by rho beta. So this is pi by 4 d alpha square into L, that divided by pi by 4 d beta square into L. So that is nothing but rho alpha into sigma beta by rho beta into sigma alpha. So assuming the costs per unit area, per unit weight, cost per weight for both materials are C alpha and C beta. So the total cost, total material cost will be T alpha by T beta, which is nothing but C alpha weight W alpha by C beta by W beta, which is again this weight, again you can convert it into density. So alpha by beta into rho alpha by rho beta into alpha, that is stress, this is beta. So you can do a cost comparison. A cost comparison is done keeping, what did you keep? You kept tensile strength for two different materials. So in the similar way, you can try, you try for compressive test, compressive strength, you try for compressive strength, and the dynamic analysis, what we were talking about is the fatigue strength. You can try this, right? So this is for tensile we have done. So what have we done? In step 1 density, then we found out the area, then the cross section is the same, because when you try to change the this thing, so we always try to take the cross section area same, then we diameter same. So from that we try to find out the load. So from the load we try to find out the diameter ratio. So then weight ratio is directly proportional to the cost. We saw the cost. So with this you can try to find out the total cost for any two given materials. How do you compare? So this is only one property. So if you have, in reality, you will always have combinations of several properties, and the biggest challenge is what is the weightage you give for each combination carries importance. So in the similar way, we can try to you can also try to do for designing a stiffness. If you want to do for bending stiffness, then what do we do? Bending stiffness, then what we try to do? We try to find out the deflections. So how do you do the deflections? So deflections can be done by load L cube by 48 EI. So where P is the load, L is the total length of the composite, and then E is the Young's modulus, and I is the moment of inertia. Okay, so we can try to do this. So generally we know in composites, I was trying to tell you that it can be made with varying orientation. For example, I said it can be made out of 0 degree orientation, it can be made out of 45 degree orientation plus or minus, it can be made out of 90 degree orientation, it can be made out of 30 degrees plus or minus, 60 degrees plus or minus. So all these things are orientation. So each one in a lamellae, so several of them stacked together forms a laminate. So if I wanted to determine for a composite material with varying orientation, so if the and then varying orientation, so here what is that is, I just telling this information does not end. So I have to also try to say number of plies I use. So that means to say number of plies or number of layers. What is a layer? Number of laminae. Okay, so number of layers, I have to also say this. So let us assume there is a composite which is made out of plus minus 45 degrees, and then we use 16 or 12 laminates, 12 layers. 12 layers for construction. So if we wanted to find out the equivalent modulus along the longitudinal direction, because yesterday I told you there is a difference in property between the longitudinal and the transverse direction. Longitudinal direction, let us assume in x alone, equivalent modulus along the longitudinal direction, x direction. Okay, so the end formula will be something like this: Ex equal to cos 4 theta divided by El plus sin 4 theta divided by Et plus 1 by 4, we can have 1 by GLT minus 2 times Poisson's ratio, Poisson's L in the, okay, LT. Poisson's ratio divided by EL divided by EL into sine square 2 theta, where EL is the modulus of elasticity. I have been using two terms, Young's modulus and modulus of elasticity. It is the same. So I will write it down. It can be also called as Young's modulus in the longitudinal direction. Longitudinal direction. Okay. Then ET is going to be the Young's modulus in transverse direction. Transverse direction. Then you will have GLT, which is nothing but the shear modulus. Now you see, now new terms come into existence. Shear modulus of the composite. VLT is the Poisson's ratio. Is the Poisson's ratio. And the theta, what we talk about is the orientation. So you see, the orientation also plays an important role as far as the cost, as far as the properties are concerned. We will try to see the stiffness of the beam. The stiffness of the beam. How do you find out the stiffness of the beam? The stiffness of the beam can be found out by this way. It is 48 EI by L cube. So where the stiffness is proportional, the stiffness is directly proportional to EI. So the two materials which we use, the two materials used are alpha and beta. So E alpha I alpha equal to E beta I beta. So the beam, now what we have done, can be I beam, it can be rectangular, it can be circular beam. So depending upon this, so you can try to change and try to find out the deflection. Just for your information, rectangular beam has I nothing but BH cube by 12. So if you want to do the height here, it is the height or the thickness you can take. Thickness, or you can take the height of the component, height or the length of the this thing you can take, height or the thickness of the cross section. So if you take two different materials, it can be H beta equal to H alpha, E alpha by E beta into half. So what have we done here? We have done the stiffness of the beam. We have tried to find out for two different materials, and just for rectangle I have given it. So if you want to do it for other beams, you can try. And what we have done is we are trying to find out the thickness of the cross section area. We are trying to find out that, and this relationship can be used for comparing two different materials. So now if you want to compare it with, initially we were trying to work on relative weight. So this is for the relative weight, and finally what we get is the total cost for this given component. So there are two materials we are trying to compare and try to find out the stiffness. So next is the weightages of properties. What is the weightages? Weightages, first we have now figured out two different materials, two different properties, and we know what is the impact of each other. So we are now trying to give weightages for individual properties, which is maximum and minimum, and then we try to come with a non-quantitative scaling property for the same. So if you look at property A, B, C, D, or these are the properties, and what we are trying to do is we are trying to compare materials. So for example, you see a chemical resistance poor, then it is good. For B material it is good, for C material it is excellent, for D material it is satisfactory, E material is good. Now what did we do? We converted all these qualitative terms into a subjective term. That means to say this is extremely poor, this is extremely rich. Then what we did was we tried to multiply it with a factor and get the scaling properties. So how did we do that? So we will try to see for maximum property. So maximum property is defined as a term called as alpha, which has a scaled property which is equal to numerical value of a property divided by highest value in the same category. Multiply by 100. So you always get to know. So multiply by 100. So what basically you do is you take a value from 0 to 100 and try to get this value. By this what we get is we try to get the scaling for maximum property. In the same way you can also do the minimum property. So minimum property is again alpha. It is nothing but scaled property which is nothing but lowest value in the same category divided by the highest value in the same category, highest value in the same category. So basically what are you trying to do? You have done for maximum, you have done for minimum, and then you multiply it with 100, so you get the value. So here scaling for the non-equator. So finally what it happens is it comes to a new term called as gamma, which is put a summation of wi into alpha I. So where w is the weighting factor, then alpha is the scaling factor, I is nothing but the summation of all properties, which you have considered. So we get a term called as gamma. So this is a non-qualitative property. See, you can do all these things otherwise. Today we have standard expert systems which are available, where in which in expert system what we have is we have a database, we have a data, and then we have this rules whatever you have framed, if and else rules, and then you get the output. You get the output whatever you want. You just put all the queries whatever you want and other things. There is a huge set of database. This database is getting iteratively improved. So what people have done is people have started building expert system. The expert system is used for material selection. In an expert system you will have thousands of materials available. The raw material supplier provides designer and the fabricator whatever information they want, and initial screening of the material can be done very fast. There are only few expert systems which are available. Again, in this expert system whatever comes, you need an expert to tweak, to change, or to modify or understand. All these terms we can understand the solution and then start doing. If an expert system is very good, the user feeds in the service condition required and also gets the best output. Based on the available material data, the expert system are also used for selection of materials. So the assignment for today's lecture will be, you can take any polymer product, right, and then try to find out what are all the loads getting acted on it. Is it only one load or is it multiple loads acting on it? And then if you find out there are multiple loads acting on it, what weightage will you give for each load, and then you will take that as a base matrix to select a polymer. And here we are not considering cost, we are just considering only loads which are getting applied. So the loads can be tensile, compressive, shear, fatigue, whatever it is, right. So with this we will try to come to an end to lecture 6. Thank you.